I think that should probably work now. I see a little light now. Okay. You didn't miss much online, don't worry. Now going over to what pulsars actually are doing, this kind of setting the stage here with these pulsar, thinking of pulsars as rulers, measuring the distance between us and the nearest pulsars. And the life of the pulsar is takes place as a simple kind of star, a run-of-the-mill star, like a sun-like star, a radius about 10 to the 6 kilometers, and a period of about a month in rotation. But at some point, it undergoes a supernovae, and that supernovae will produce a much denser star, a neutron star, with a radius of about 10 kilometers. Now, by angular momentum conservation, you end up getting this rapidly spinning object of periods that can go down all the way to a millisecond. Now, the reason why this is useful is because these also act as flashlights. They have beams, a certain axis at which they beam at, and they're emitting pulses of light at us about every millisecond that we can track here on Earth. And that's what we do. We observe each pulsar about once per week for about an hour. We don't have the capabilities to do this continuously. And you can build plots as are shown here for intensity, and your telescope is a function of time. So you see a bunch of different peaks here corresponding to one pulsar whipping around and hitting our telescope, or like that pulsar hitting our telescope at each of these characteristic times. And you can label these pulses n equals 1, n equals 2, n equals 3, and then label now the time of arrival of each of these pulses that are arriving at your telescope. So you make plots as shown here. And if you had a perfectly oscillating spinning top of this pulsar, you would have just a straight line here corresponding to the time of arrival of the nth pulse going as the number of pulses times the period. And what you really want to do is fit away this deterministic motion of the pulsar, so to speak, and build residuals, delta t's, as a function of these pulse numbers. And these are what you want to use to try to look for new physics outside of the pulsar's oscillating motion. And using this, you can try to now build a ruler which stares out into space about the distance from the Earth out to these pulsars. And the idea is if the Earth moves a little bit closer towards this direction, you'll see light pulses a little bit more frequently. It moves away, you'll see them less frequently. And as you can try to now, over time, detect motion of this observer relative to the pulsar. And if you have, for example, a gravitational wave, the context of this workshop, you can now oscillate the Earth back and forth as a function of time, and you try to look for those oscillations with your experiment, which will be imprinted now in these delta t's, your residuals. Now, a typical pulsar is not perfectly stable. Instead, it kind of fluctuates back and forth on a time scale, if you're lucky, of about 100 nanoseconds just by various effects in the pulsar system. So what you really want to do is try to knock down these error bars by correlating time series from one pulsar to another pulsar, and then trying to use that as a way to look for a gravitational wave. Because the gravitational wave will shake just the Earth to a good approximation. You can just forget about the pulsar's effects with the gravitational waves and focus on the fact that it'll shift the Earth back and forth. And noise will just kind of contribute for each pulsar itself. So the correlators between two different time series are really what you want to try to use. And there's a certain angle which determines that time series correlation function, which I'll come back to. And you want to try to check that it's consistent with gravitational waves. And now you cannot look for motion of the Earth for arbitrary frequencies, but instead you can only look in a certain window. And that corresponds to motion back and forth with about an inverse decade in frequencies or up to an inverse week. And I'm going to call that the pulsar timing window. And that just means that you're looking for a pulsar, remember, once every week or so, and then you're doing this for a span of a decade. So that's kind of setting this frequency range. Now, you might then, the next step is to wonder what sort of sources of gravitational waves really produce.
What's determining the weekly upper bound? Is it just money, data, like some bandwidth problem, or something more fundamental?
It's money. In terms of trying to actually look more frequently, it's an issue to look more frequently, but you're also more and more sensitive at the lowest frequencies. So just practically, it's less interesting to look more frequently because it's very hard to look at high frequencies. So I'll show you plots of sensitivity later on, and they're going to fall off with frequency very fast. Good. But then the next step is to understand what are the sources of gravitational waves inside this PTA or pulse timing array window. And you can do that by just staring at certain binaries and asking what is the frequency of emission for a given binary. Now you get in this 10 to the minus 8 hertz, or this kind of inverse year range relevant for PTAs, for masses about 10 to the 9 solar masses. if you have a separation of about 0.01 parsecs. That corresponds to supermassive black hole binaries, which can be at these sort of radii, as I'll discuss in a moment. But to understand the signal you want to have, we need to understand why you would expect these supermassive black holes to be at such short distance scales, about 0.01 parsecs. And then you have to understand their evolution as they evolve in time. Now, supermassive black holes don't come as bare objects in the sky. They have accompanying galaxies. So a supermassive black hole binary corresponds to two galaxies that are also merging. And let's now study how these objects will take place as a function, or what they'll do as a function of their separation. And the key to understanding this process is to understand how they'll lose energy as a function of distance, because these are very kind of large binding energy objects, and they have to lose a lot of their energy to get back to these very, very small distances, which will correspond to 0.01 parsecs at the end of the day. So the first process that takes place that tries to, or that it's able to eliminate the energy of these black holes is dynamical friction. The idea here is that you have many stars that are surrounding the black holes. They're fast-moving objects inside these slow-moving stars, and the stars clump in the trajectory of the black hole behind the black hole, pulling it backwards. So this process is called dynamical friction. It's able to take these binaries from being very far away, perhaps megaparsecs or further away, all the way down to about 10 parsecs. Now, what really happens for smaller distances is actually a very tough problem. It's known as the last parsec problem. And the point is that you just don't have that many stars that you expect to be within binaries at these sort of distance scales. So dynamical friction is no longer expected to necessarily be as efficient as it will be above about 10 parsecs. And there's different ideas about what's really happening here. But the most pessimistic idea is that they just stall. So two binaries lose energy, lose energy, lose energy. At some point, they just stall at a certain distance. And up until the point that a third binary or third black hole comes in and kicks them. And that's kind of the most pessimistic situation, because it takes a very long time to reach this next regime that I'll talk about. And I'll show you kind of plots that take this assumption versus other assumptions people have put in the literature. But regardless, they do get to the smaller radius, this point about 0.1 parsecs. And then you have a new way to dissipate energy, and that's through gravitational wave emission. And that's really what you want to look for. Gravitational wave emission first circularizes the binaries, which come in often with high eccentricities right in the beginning. And then you reach this kind of dominated gravitational wave emission regime. And that's really the part that's going to be inside this PTA window that I'll be discussing today. Now, at some later point, these things will lose so much energy that they'll actually be hitting one another. You reach the innermost stable orbit when these things combine to form just a single black hole. But this is kind of the era that I want to study, and I want to discuss kind of how you can use this era to probe particle physics, which might seem like a very daunting task because there's so much complicated stuff here. We don't even understand this era at all. But what I want to argue today is still this is a fairly clean era and has some prospects to use as really a laboratory for particle physics. Mm-hmm.
So to what redshift can you see these things?
So the redshifts that we're going to be using that will be kind of in this range will be a redshift of 1. So it's very, very nearby supermassive black holes.
So then why is that pessimistic? Because for instance, I could envision a case in which your supermassive black holes are actually merging very early on because there's an efficient process that is making them merge, making them to go to the center. And then everything happens at redshift, say above 3, and then you don't see anything now.
Oh, because they're all gone, but you still have other supermassive black holes that are contributing, right? There's a hierarchical process. It's not just supermassive black holes and nothing else. You have always other black holes that are lower and lower in mass. So if you have one black hole, I mean, there's more coming up. So if you merged earlier, you would also have more that are kind of in the train.
Well, yeah, I guess that. Oh, well, yeah, but I could envision a case where most mergers happen very early on, right?
I mean, you would always have situations where kind of there's more merging that's happening. There's no notion at which it would stop. There's no reason for the things to stop merging, right? You'll always be able to kind of just by chance over time just hit more binaries, hit more binaries. There's no notion of like, there's no end point in this process.
Till we are all in one black hole.
Yeah, we're not there not there yet at least, yeah. Okay, so that's the next step of this talk. I want to understand how you can use these supermassive black holes as environments to study particle physics. And to do that, let's first go to look at the parametrics here. Just to kind of set the stage here, we're talking about distances about 0.1 parsec to 0.01 parsecs in the PTA window. The Schwarzschild radius of these things is much smaller, about 10 to the minus 4 parsecs. So there's a nice separation of scales here that I'm going to talk about in a moment. And the reason why these things are hopefully a good environment to study particle physics is for two reasons from my perspective. The first one is that there's very high energy particles that are sitting around these black holes during their history. Every supermassive black hole that we know about is expected to have gone under some period of having very powerful jets that are surrounding it. And these powerful jets can accelerate particles to a GeV to a PeV of range, depending on your assumptions about what's taking place inside these jets. So it seems like from a sense of kind of trying to probe the electroweak scale, it might be an opportunity in this way to try to probe these sort of collisions inside these environments. The second reason is that supermassive black holes are not bare point particles, but instead come with a dark matter halo, just like the black hole that we have in our Milky Way comes with a dark matter halo. And hence, maybe you can use this environment to try to look for dark matter interactions inside these sort of mergers. And the case that I want to describe today is looking for new long-range forces. It's a nice, simple test case that I'll describe to you today, but perhaps you can also look for other effects that are beyond the scope of this talk. Now, the first thing that you might imagine happening is that these high energy collisions are producing new particles. Here, I'm calling it chi and psi with some new scalar mediator with a dot here, a dash here, sorry. And the system will charge as a function of time if these particles don't have the same mass. And what's happening is that one particle can escape because, let's say, roughly massless, while the other one has a mass that could be important, and it's just keep getting trapped inside this system. On the dark matter case, you can have dark matter that has self-interactions that are very large. We don't actually have any handle on dark matter self-interactions that are significant for ranges about a kiloparsec and below. That's kind of the range at which we are kind of probed these things before in galactic dynamics. We've yet to really have any information on the sub-parsec or even sub-kiloparsec scale. Now, this is all heuristic. You really want to try to kind of take these things and put constraints on particle physics models. I'm not going to do that today. Instead, I'll just make some very simplified assumptions. I'll assume some mechanism took place that produced a charge on these black holes Q. I'll assume that as these things are merging, the charge is independent of radius. So you might imagine that's actually not true, but you're penetrating into some cloud of particles that are surrounding these black holes, and hence Q will be a function of R. But I'll take it to be simply just equal to Q, equal to a constant as you're emitting gravitational waves and getting closer and closer inside the binaries. And I'll also make an egregious assumption that all supermassive black holes carry the same charge parameters. And I'll talk about what that means in a moment. Again, just for some simplifying my analysis. Now, this is just a very simple point. You'd have to really address these things to set constraints on models. But there's some sort of checks that you need to make anyways to make sure that you're doing things sensibly, that you're consistent inside your analysis. That's what we did. You want to make sure that if you have charge which is infalling right on the black hole, so not in a cloud surrounding the black hole, then you have things like no-hair theorems that tell you that you need to have a vector mediator, not a scalar mediator, that's governing your dynamics. Black holes can discharge charge as a function of time if some sort of vector mediator has a mass. So you want the mass to be sufficiently small. And you also make sure you do not satisfy, or you do satisfy extremality constraints on black holes, which tells you that the Q here, this charge, is less than about a mass over m Planck. Now, if you have particles that are surrounding the black hole, some sort of cloud, so it's not on the black hole itself, then you still need to satisfy some constraints. One of them, for example, is if you have a repulsive force, if you have some test particle inside that cloud, it should be bound to the cloud instead of being kicked out. In that case, you now want to set things like the gravitational pull on this test particle equal or greater than or equal to the repulsion this particle will feel. And that sets for you an upper bound on the amount of charge that you can try to accumulate onto this system. And that ends up actually having the same condition as you would have for extremality. So you always want to imagine a situation where Q is less than m over m Planck if you want to be consistent for repulsive forces. So let's go over the dynamics for these charged black holes. And I want to set the stage with a single merger. And then I'll go over the case that I really want to talk about, the stochastic background of gravitational waves that I'll discuss in the next slide. So if you have some sort of Earth system out here staring at pulsars far away, and you got some supermassive black hole, which is perhaps 100 megaparsecs from you, it's merging and emitting gravitational waves. Now, the force that comes into merge things together is just Newtonian gravity, just equal to Gm1m2 over r squared. The power, you know what it is, just by general relativity, is given by this formula over here, which scales as omega to the 6 times r to the 4th power. It's the quadrupolar radiation from general relativity. Now, you can understand dynamics of the system very easily by just setting the force that's pulling these things inward equal to centripetal force that is being used here, mu omega squared times r, and that gives you Kepler's law. Omega squared is proportional to 1 over r cubed. You can also understand how the distance separation changes as a function of time by setting this power emitted by gravitational waves equal to the power equal, or the energy change in the mechanical energy of that system. And that gives you what is the dr dt, the separation as a function per unit time in terms of these kind of gravitational parameters. Now, as you might expect, if you have some long-range force, you will modify this picture. So it will no longer be as simple as this. But in this first case over here, I should first say that you have a very simple scaling of frequency as a function of time. And this is also what LIGO found for black hole neutron stars or black holes that it found inside its system, because everything here is still the same thing. I mean, I'm just scaling it up for supermassive black holes, but we already detected these sort of effects for the case of LIGO. Now you can try to look for how this effect will impinge on a time series if you really have some supermassive black hole which is nearby. And you'll see simple oscillations as are shown for you in this top right-hand plot. You'll have a simple sine oscillation that's hidden inside your data. Now, of course, in practice, this is much messier than what we're seeing over here. You have a very small signal over a very noisy data set. So I'm kind of blowing up for you the signal, so to speak, to try to see a nice effect. Now, if you want to discuss charge mergers instead of just pure gravity mergers, this has kind of been a topic of our work, and it's also been kind of considered in the past for black hole neutron star interactions back in 2017 and follow-up papers as well. And there's kind of two major effects that take place inside these mergers. The first one is a force that's new now, not the gravitational force, but a new kind of force, which I'm parameterizing here by some value of alpha, which is just a force strength parameter normalized to gravity, just given by Q1, Q2 divided by the gravitational force constant out front. The second effect is you have now dipole radiation that you can emit in addition to the quadrupolar radiation into gravitational waves. In this case, the power is given by the Larmor formula that you study in undergrad, given by these omega to the 4 dependence out front here. Now, some sort of fundamental parameter here, which is called gamma in my notation. It's a charge to mass ratio difference of these two black holes, again, normalized to gravity. So there's two parameters that I want to discuss, these parameters alpha and gamma, and they're the things that I'm going to be trying to constrain using the upcoming data set that I'll show you. And with that, we can now move to stochastic merger. So not a single merger, but instead summing over all the different mergers that are happening all around the universe around us. You can still go ahead and try to use the same Earth pulsar system, of course. Now you just have many different black holes. Each one is sitting at a different frequency, and they're going to have a different amplitude. And you want to sum over all of them to try to understand how large a signal you'll have here on Earth. Now, in this case, you have a much messier looking system. You have to sum over all the different sources when trying to understand your residual as a function of time. And you might think that it's a kind of unmanageable problem, but in fact, in the limit where number of sources goes to infinity, you have a very simplified calculation that you try to do to estimate what is the signal you'll see inside your experiment. Now, the observable that you want to try to use is the now correlation functions of delta t's. Delta t by itself is not so useful anymore. But you can still use this kind of delta t correlation function of different pulsars. And that's roughly equal to the characteristic strain that's often discussed in the context of interferometers. You can also use it in the context of pulsars. And it's related to the energy density in gravitational waves, rho GW. Now, this energy density in gravitational waves, this quantity here, per unit log frequency, technically, is given by a very simple integral, as was discovered back in 2001 by Finney. I don't have a reference here. But if you assume just two things into the system, that you have isotropy in the universe and inhomogeneity in the universe, you can now split the integral into this kind of simple form, where you have some integral over the different masses of black holes, some redshift dependence here, and two important functions. One of them is shown in red here. It's called the co-moving black hole distribution function. How many black holes are sitting at some redshift around us today with a given mass? And a second term here, which is in blue, the energy which is emitted per unit log frequency of a particular binary. Now, the key point that I wanted to try to claim today is that this term right here is very messy, has to do with astrophysics that are kind of beyond our ability to get a handle on at any sort of order one level. But you have this second term over here, this dE log f, which is kind of a fairly clean quantity. And most importantly, it's where all the frequency dependence of this function will sit in. So we can try to use the shape of the curves that we're going to detect soon as a way to probe particle physics. And this will also be modified by Q1 and Q2, the charge of these black holes. So let's stare at this function a little bit more carefully and take these different terms. The first one out front here, this kind of messy one, we followed some work back in 2013 and how to calculate it. There's been different efforts, different uncertainties that are involved here. And there's easily order 10 uncertainties that are kind of sitting around when trying to understand this, this quantity out front, perhaps even order 100 uncertainties. But for one set of fiducial parameters, you get these kind of plots shown here on the left-hand side. So coming back to Daniel's question about when these sources are actually taking place, here you're seeing that most of these black holes have the kind of these large masses, about 10 to the 8, 10 to the 9 solar masses, for redshifts that are almost of order 0 here, 0.1 or 0 roughly. And if you can blow up here, you'll see it's actually not quite at 0, but it's a little bit kind of shifted away.
So how do we know this? So I guess that the calculation of how many binary mergers we have depends on galaxy mergers. So how often do they happen, which we probably don't know very well. And then how much time does it get for the black holes once a galaxy merge in order for them to get together, which we also don't know very well. So actually, how do we know this?
Yeah, so certainly there's big uncertainties. They do exactly the way that you said. So they stare at galaxies out in the sky and they assume that each galaxy carries a black hole. And they use that to try to infer you have this sort of map between black hole to galaxy features, and then use the galaxy that we observe as a way to try to probe how many binaries we have.
Okay, so is there a so this is just purely hypothetical, but for instance, is there a scenario in which there could be a small number of galactic that is consistent with data, that there could be a small number of galactic mergers for redshift lower than 1, which is what you're looking for, so that the rate of supermassive black hole mergers is essentially close to 0 for those redshifts?
So I'm going to show you in a couple of slides the prediction for kind of what's called the most pessimistic prediction for PTA sensitivities. And there they assume that, yeah, you have the stalling behavior, which is going to be the worst case scenario, so to speak, for how much signal you can have. And they try to marginalize over all the different possibilities for galactic mergers. It's not my work, but I'll show you the result at least kind of in that case.
Thank you.
What's called the lower limit, so to speak, of these analyses.
So this is purely empirical, this one.
This is purely empirical, yeah.
Is it consistent with like the larger black holes at redshift being the product of earlier mergers? Like, has it been compared to a model, like a merger model, or like a population synthesis model?
Yeah, so this one right here, I mean, they do this empirical test. Whether they compare it to models, presumably they do, though I don't know how the comparison plays out actually.
Okay.
Yeah, most people from the astrophysics community, they're really looking at the other way around. They're hoping that using a PTA analysis, you can try to learn about black holes. For us, of course, we're interested in going the other direction. All right, so that's this first term out front, kind of this messy term that I'm not really going to address. The second term, this one over here, is where particle physics can really try to modify. And that'll be in the spectral shape of this curve out here. Now you can try to calculate it fairly simply. So you can try to dE in gravitational waves per d log f, of course, depends on dE d omega, where omega is the angular frequency of the system. And it's given by just the chain rule versus parameters that I've already discussed for you. So it's equal to dE dt, or the power in gravitational waves, dt dr, the separation per unit time, and dr d omega given by Kepler's law. So you can see that every term here I've already described for you in the case of the gravity-only mergers. In the case of charge mergers, you got to modify each of these appropriately, but it's a pretty simple exercise to try to do that. So it's not really too hard a problem. So each of these terms are kind of have a handle on once you assume certain charges for the black holes. Now, in the gravity-only case, you'll find that this quantity over here just goes as omega to the 2/3 power. I'm not showing you that here, but that's what the result turns out to be. And hence, you can try to calculate then what is the characteristic strain, which is proportional to the square root of rho GW versus over frequency squared. And you'll find that it scales like f to the minus 2/3. So this is the kind of the big prediction for the supermassive black hole mergers for gravity-only cases. And that's what we want to try to modify. So let's stare at this curve now. Here I'm plotting for you the characteristic strain HC is a function of this frequency f here in this 10 to the minus 9, 10 to the minus 7 range that PTAs can kind of try to address. And the gravity-only mergers line is this minus 2/3 curve that I'm showing you in the center of this plot. Now they parameterize it in a certain way. So there's some sort of amplitude AGW versus frequency to the minus 2/3 normalized to an inverse year. That's kind of standard inside this literature. Now there's a few effects here that this is neglecting. At very low frequencies, you expect circularization to be important. So the binaries can still be eccentric. At very high frequencies, beyond this plot here, we're looking at the ISCO frequency, where you'd have a cutoff inside the spectrum. And as I've already mentioned repeatedly, there's an uncertainty that's very large here in the amplitude of this line. So whether it's actually going to be here or here is not very well known. Now, what I was hinting as Dana was asking this question, that there is some sort of effort to try to understand the lower limit on this quantity. And that's what these folks did here in 2017. And they claim this is the most pessimistic possibility. So that's kind of the lower limit case and the kind of the key point they tried to emphasize that's well known in the pulsar community is that using this kind of future SKA-based detectors, you should be able to probe this most pessimistic case. So they believe that there's almost kind of a no-lose theorem for these sort of experiments when you start scaling them up further and further. Now, we've already been carrying out these analyses for quite some time. Here you're seeing one analysis for an 11-year data set by the Nanograv collaboration. That's their limits. You have these other collaborations like EPTA and PPTA, which are also putting constraints in this parameter space, and they're digging into my beautiful black curve in the middle of this plot here. Now, what happened back in January was a big revolution inside this field, at least it might be the start of one. And Nanograv released a 12.5-year data set. This is the newer data set that they released, and they fit for this sort of curve inside their data. And they found a signal. So here you're seeing the posterior of this sort of search for this sort of power law inside their data. And they're plotting here, the posterior is a function of this amplitude AGW that's parameterized as shown here. And you're seeing that you strongly favor some sort of process among the different pulsars with an amplitude about 10 to the minus 15 or a little bit above in size. So it's kind of the updated version of this analysis right here is now the leading analysis, and they seem to be finding some signal. Now, there's a lot of effort to try to understand if the signal is real, and that's ongoing right now. One check they did inside their paper is to check whether the angular correlations of pulsars matches the one you'd expect. Remember that we're looking at quadrupolar effects here inside the signal. So if I look at some black hole here, some black hole here, there's a different correlation factor depending on the value of my the pulsar separation. Sorry. So pulsar here, I should expect a different value versus pulsar here. So you can try to look for these correlations in the sky, and that's what they did in this plot out front on the right-hand side. Now, if you had non-quadrupolar angular correlations, then you would have this yellow line. Quadrupolar is this blue line. Dipole is in between the two, so it kind of is still a possibility that they have a dipolar correlation function, and they're kind of trying to narrow this down as we speak. And one thing which is also ongoing right now is the other collaborations are combining their data into this international pulse timing array, and hopefully they'll be able to also detect and confirm the signal, which would be a remarkable discovery, probably one of the biggest in our field in the last few years. Now, the part that I want to discuss is looking at these charge mergers. And there's two major effects that I mentioned for you before. One is adding in a new force between the binaries. That's what's the effect that I want to study in this left-hand plot here. Now, you're going to have normally a force and you'll have a radiation concurrently, but I'm going to focus on one effect at a time. In reality, you'll probably have both. Now, adding in a non-zero force corresponds to adding in what I called a non-zero alpha parameter earlier on in my talk. Here I'm showing in the gravity-only curve as the black line, and I'm going to put on top of this curves that have different value of alpha. Now, there's a key point which corresponds to the mass of the mediator, which plays a very important role for the case of a new force, because it kind of creates for you a cut inside this plot, or a kink inside this plot, corresponding to when the radius or the separation of the binaries of order the inverse mass. That's when the force turns off. Now, if you plug in values for what is the radius as a function of time, you'll see the frequency that corresponds to this point over here is about 10 to the minus 24 eV, for a mediator about 10 to the minus 22 eV. There's a factor in velocity that separates these quantities and this quantity over here. And regardless, what you find is, of course, a difference in this curve out here for different values of alpha. Here we're seeing me jacking up alpha to almost an extremal black hole, and you're finding that we're seeing a larger and larger effect modifying the slope here. Now, again, you're never going to be able to detect the fact that you have a different amplitude inside this range here. The key point is that the spectrum changes itself, so the frequency dependence changes. And once you make a detection, you can now put a pretty firm constraint that there's no charges if you really find this beautiful minus 2/3 behavior that you expect. Now, if instead you imagine adding radiation to this process, not a new force, in that case, it's parameterized by what I called the gamma parameter earlier on. You have the minus 2/3 curve. If you now have a massless mediator, you still have an effect because you have dipole radiation instead of quadrupolar radiation. That's good enough to modify the spectral index inside your experiment. And you're seeing the value for different values of gammas is changing this slope of this curve. And if you have a massive mediator, you now put a cut on the spectrum when the frequencies of order the mass of your mediator. Now, we can now compare over the observations because Nanograv also produced for us a value for what they find is the best fit amplitude as well as index. So they were also doing an analysis where they float the index of this power law. And that's given by what's shown here. So amplitude on the vertical and the index shown here on the horizontal. Now, if you have a gravity only case, you have a straight line here. This is the prediction for gamma equal to 0 at minus 2/3. This is the result that Nanograv found. So they found a result which is consistent with minus 2/3. But not necessarily it's within the 2 sigma range of their curve. There's a technical kind of point here, which I don't want to address, but you can ask me about it afterwards, about how they carried out this particular analysis. Now, if you start to crank up the value of gamma, you'll change the spectral index, and then you'll get a value which is 0.2, 0.4 here, which will correspond to kind of pushing these lines further and further to the right. And so you can imagine that if we kind of keep pushing gamma above, you'll now be able to put a bound on what is the value of gamma. And in general, you'll have to do a more careful analysis because we're taking a power law form, which doesn't actually fit very well for this different charge parameters that I showed you in the previous slide, but it's still approximately a power law. So this still makes sense to kind of make these sort of plots. And we're hoping that the PTE collaborations will try to now in the future make curves like this to put constraints on these values of alpha and gamma and the mass of the mediator if new charges really exist inside these systems. And with that, I want to conclude. So supermassive black hole binaries, hopefully I convinced you, are kind of a new upcoming laboratory that have some perspective to try to look for new particle physics effects. There's one clean observable, which is a spectral index. That's really what you want to try to use to try to look for new physics. And this kind of new long-range force that I discussed for you is one possibility as a test case to try to look for probing new physics inside these systems. It'll be interesting to understand other possibilities, like if you have super radiance inside these black holes, you'll now have a mass dependence as a function of distance. You can try to use that, or you can try to use other features and other possible ideas. Trying to use this kind of binaries for particle physics would be hopefully a nice kind of opportunity for all sorts of new physics, maybe on the TeV scale direction or on the very light particle direction, or perhaps both. And with that, I want to come back to this timeline that I started off this talk with. We had these kind of big developments back decades ago, and I would argue that we're kind of entering this new range right now back in 2021. We're potentially discovering these supermassive black hole mergers already in the current data. Maybe it'll tell us something about dark matter, about the TeV scale. And the big future in this business will always be will always be kind of in this futuristic telescopes that are upcoming in 2026 and beyond. Things like the Square Kilometer Array, the FAST telescope. These are big projects that will be happening for decades to come. And they'll be trying to understand these spectrum and getting these things down to precision science in the near future. Thank you.
Any questions?
Yeah, it's the fact that these black holes have very powerful jets inside their history that can produce particles that are up to a PeV in energy. So if you have those sort of systems, you can imagine trying to probe the TeV scale with their collisions inside these clouds. It's one of the unique features about these environments that they're carrying just really gigantic energy particles.
I want to ask a question about the same plot, actually. The
NDM1.
The empirical. Yeah, I was just because this is actually the first time I heard about the final parsec problem, and I was just wondering if this assumes something about the final parsec problem.
Yeah, it does. It does. So here the assumption is there's some sort of gas surrounding the black holes that are enough to drive you into this gravitational wave only regime. Okay. More generally, you'd have to, for other cases, you have a different plot like this. So for every model you have in mind, you would just kind of make these sort of plots, and then you would build the curves from there. So we chose one of them for this curve, but kind of these folks over here that made this plot, they varied over many different models to build these sort of curves.
So this most pessimistic scenario, that's like with the third person, like the third component that shoots at the. Yeah. Okay.
So you have these two binaries, they kind of are stuck for a long time, and then the third binary comes in and jags them together. Okay.
When you were showing the bounds here in this slide, I think if you click a bit more, yeah. So do you know, or maybe you explain it, what's the reason why there is such a weak spot there at a specific frequency for all the bounds?
Sorry, what was the question? Oh, here?
Yes.
Oh, yeah, it's actually a pretty neat point. It's that this is an inverse year, and things are hard to do at an inverse year because the solar system has that sort of time scale too. They have to do things like fit away all the dynamics of the solar system to do these sort of plots. So anything that kind of takes place at an inverse year is hard for them to try to probe. So they just lose sensitivity around this range. Yeah. And then coming back to Raffaele's point earlier on, you see the frequency kind of is falling off as you go to higher and higher frequencies. So trying to go to beyond an inverse weak is kind of tough business because you're just so far and far in this tail.
Again, because of the background, so like Earth-Moon dynamics.
The Earth-Moon stuff is what sets this problem. The frequency scaling is actually different. It's because they're not really measuring, they're measuring delta T correlators, not frequency correlators. And there ends up being some kind of subtlety in the fact that you get some frequency squared in the noise. Like PTAs are white noise, pulsars are white noise when you're looking at delta T correlators, but they're not white noise in these sort of plots. It's some sort of technical point, converting a strain, characteristic strain to delta T that I didn't really emphasize. But you can predict the scaling analytically.
Can I ask a question from Zoom? I don't know. I raised my hand. I don't know if I can.
Sure, go ahead. Sorry, I didn't see it.
Yeah, sorry. Hi, Jeff. It's Andrea Caputo. Thanks a lot for the talk. It was very nice. So I have a question, actually a couple of questions. So first of all, you're working in the Newton approximation, right? But you're dealing with mergers. So likely like post-Newtonian correction will be very important, right? And this, like if you estimated that, like accretion, but even other effect may be really important, especially during the last stages, right? And second,
so you're very far from that point. So you're nowhere close to the ISCO radius inside these systems. It's very different from LIGO, where you're actually seeing the entire merger. The effects that we're seeing are actually in this kind of very early regime. In fact, the black holes don't even merge inside. I don't know. I'm looking up. The black holes don't even merge inside the lifetime of an experiment. They're going to last indefinitely. So they just go around and around and around, even for the entire decades that you're staring at these, you're sensitive to these sort of black holes. So you're actually very, very far apart, well before any post-Tony corrections will be important.
Okay, that makes sense. And then the other question is like, I would guess that at least for some frequencies, given that you have very, very few sources, Poisson noise would kill you, or at least like be important, right? Did you consider that in the analysis?
Yeah, that's an important point. So they actually have, there's definitely an issue. So if you're looking at these sort of plots here, indeed, if you're looking at high frequencies around here and above, the Poisson noise is going to be a problem, and you'd be concerned that maybe you're kind of not seeing a continuous spectrum, but seeing instead finite sources that are going to muck you up. And it's true, that is a concern. Inside the sort of intermediate regime, kind of at these lowest frequencies, you're in that safe zone. So definitely the high frequencies of this plot are more scary. The lower ones, you should be okay with Poisson noise.
Okay, great. Thanks again.
I just want to ask about, so you introduce a new thermal particle, I guess light particle, then you put a coupling alpha or gamma, which I didn't understand. There aren't other bounds on this coupling, or the best bound we can get is from seeing the change of the spectrum. Kind of, no.
So well, the model that I presented is fairly arbitrary in the sense that I didn't say anything about how it's actually charged. Now, what you'd really want to do to set a bound on a model is to explain the charging mechanism, and then you would have to be worried about the effects that you're talking about. But if you're just, I didn't even explain to you how these black holes are charged. In that sense, there's no other constraints because there's no other comparison here. So the best constraints are indeed from here because there is no other kind of
But in practice, what model are you bounding? Like
these are two that I've kind of motivate the parameter space that I have in mind in terms of how you would charge these things from. But in practice, you'd have to kind of to set a constraint on massive particle versus coupling is a lot to go that we did not try to address.
Okay. Thank you.
But that's something that we want to do in the future. That's really where the big program would be. Absolutely.
Yeah, it's actually, I guess, the same question. I missed the expression for gamma because in the end, all of the particle physics goes into gamma. And I was just wondering, what kind of intuition, what's a big gamma? What's a small gamma?
Yeah, good. So gamma and alpha are normalized such that they're all relative to gravity.
Oh,
so here you have alpha Q1, Q2 over M1, M2 with a G up front. And similar to here, you have an M Planck.
Alpha, I know. That one I used as well. But
yeah. So the gamma is a charge to mass ratio difference, but I put it in M Planck here. Okay. So it's dimensionless. And then gamma of order 1 is kind of detectable in large.
But you're assuming here this only switches on after the final parsec problem and everything before. So none of this influences the formation of the binary.
Good. So here I'm looking at gammas and alphas that are well below 1 in practice, like 0.1 or so. So hopefully that's not really a major effect. In a sense that the dynamics here for the merger are not primarily set by the new force, they're primarily set by this by gravity, and then this is some sort of small modification on top of that. Now, of course, when you go to gamma and alpha close to 1, you'd be concerned about that, and then you have to worry about whether you're interesting in that physical parameter space or not.
Yeah.
But if these parameters are less than 1, you're not really going to affect this thing too much.
Yeah, I mean, you can switch on the force like late. No, you can have you can have a force that only switches on within a parsec.
I think it would go the other way around. No, actually, no, you're right. Sorry, you're right. You could do that in principle as well.
Yeah.
Yeah. So if you choose your M to be about 10 to the minus 24 EV or something, it might turn on just in the gravitational wave domination era.
Yeah.
That could be possible. Yeah.
Any more questions? Not, well, we can thank Jeff again.